Okay, hey everyone. Today we're going to talk about logistic regression and cross entropy and try to figure out what's going on there. We'll be working with Robert as he kind of has some questions and hopefully we can answer them all. So yeah, let's just jump into it. So I have a notebook open and I just have a couple of vectors defined in NumPy just to give us a little sample of what's going on, but don't worry about it too much, the actual numbers. Okay, so yeah, Robert, it's on you. So what do you want to start with first?
Okay, so I guess let's start with the regression equations for logistic regression and classification. Looking at
equations.
the
So cross
there's the
entropy.
equation. Yeah, cross entropy and how it relates to the sigmoid function.
Mm-hmm.
Yeah.
Right. So first of all, with logistic regression, you can kind of see that these numbers are like -2 and 0.5. In general, these are called the logits, or the thing that's like output from the model. To convert them, because like with logistic regression, it's a classification algorithm, right?
Yes.
So
yeah.
At least for now, we're going to think of it as a binary classification problem where you just have, predict either 0 or 1. And so all you really need to output is like a probability. So there needs to be some sort of methodical way to convert a logit like this guy into a probability. Does that make sense? Or at least that's the problem.
Yes. Yeah.
And that's the so-called sigmoid. So let's actually program it. There we go. We'll probably know the answer to that one. So how we do this is we would apply sigmoid, let's just test if it works, to the logits vector, and it would output probabilities. Now they're numbers between 0 and 1. So it converted a number like -2 to a number like 0.11.
Yeah.
And actually, let's plot sigmoid using SNS just to see what it looks like. This I want np.len space. Let's do -10 to 10. I think we need like 100. And then we'll make these the x's. I'm just going to plot the sigmoid from -10 to 10. It kind of looked like this, which maybe looks familiar. We can even do it a bit, maybe a bit more pronounced. So we'll just do from -2 to 2. Oh, it almost looks like a straight line from -2 to 2. Actually, you can see at -2 on the x-axis, it's like about a little over 0.1.
Yeah.
And that kind of matches up with this guy. This was like about 0.11.
Yes. Yeah. Yeah.
And that was -2. But it kind of flattens out pretty quick.
Yeah.
So let's do -5. Maybe that's the sweet spot. That flattens out towards 1. So you can see the y-axis is between 0 and 1. So because it's intended to do a probability.
Yeah.
Now, you could ask like, why are we using this function? Why is this a good one? Yeah, I wouldn't worry too much about that.
Yeah.
There's some justification, but yeah, I wouldn't worry about it.
Yeah. Tan H. We want to use tan H instead.
Well, tan H is in between -1 and 1, so.
Yeah, I was just talking. I just know it's in the.
Well, we could do 2 times tan H minus 1. Or maybe no. Tan H plus 1 divided by 2.
I just know that tan H is using the neural nets as a activation function as well. So.
But yeah, here's the sigmoid. Okay, so then your question is, what about cross entropy?
Yeah, so we get so then for our prediction, it's the soft max of the probabilities.
Well, okay. So there's the cross entropy, but softmax you only really need if you have more than one, like more than two classes.
Okay, yeah. So yeah, but here,
Here we just have two classes. That's kind of our setup.
yeah,
So we just need this outputs the probability. So this is like saying it's 62% chance it's class one, and the remaining percent for class
0.2,
zero.
yeah, is class 0.
So, but for only two classes, you just need one probability. But when
Wait,
you
that
have
doesn't add
many
to
class,
1.
no, this is it's a vector because this is like your first data point here,
Oh, okay,
and this is like your second data point.
yeah,
So this is like the probability that the second, or sorry, this one I highlighted is probability that the first data point is class one,
oh, okay, yeah,
and this one's
okay,
probability that the
good, yeah,
second, yeah,
is class 1.
that's right.
Yeah, okay, yeah,
So for logistic regressions, classification, and yeah, when it's binary or when there's two classes, you only need one probability.
yeah. And how do we get that? Yeah, so we get that one probability. That's what we take, and that becomes our prediction. But then our
Yeah,
cross
so
entropy
yeah,
function, which is our
yeah,
loss function, that involves the logarithms. That's where
yeah,
like
that's
logarithms,
this guy here.
like, yeah. Okay, so if we were to write that out in like latex formation, we would say what?
Yeah, right. So GitHub Copilot might do it for me. So y hat y and y. Let's see, equals. See if it's right.
Okay, cool, great.
It's not
So
quite right, unfortunately. It looks almost
okay,
right.
yeah.
Actually, can you see what was wrong or what was missing?
Hold on. There's no error term. No.
No, not quite.
Oh wait. Plus, 1 minus yi.
Yeah,
No.
exactly. One minus.
Yeah.
You have
Hey, I
to.
did
You
get
have.
it.
Yeah, exactly.
Yeah.
You have to add. Basically, that was like. I'll explain why we have to add this and what's going on in a sec.
Yeah, and there's something where like they actually zero out or something like that.
Right. So yi can only exactly they get zero out. So what they mean by, or what you mean by
Yeah.
that probably is that yi can either be 0 or 1 because it's a binary classification problem.
Yes.
And yi is the target variable. So that's what we're trying to predict. So if
Yeah.
yi is 0, this first term disappears because yi is 0 and 0 times anything is 0.
Yeah.
However, if yi is 1, then the second term disappears.
Second guy disappears.
So
Yeah.
regardless, one of them is going to disappear. So that's what.
0.
So half of
Yeah.
the one out of the two
If
terms are going to disappear.
0 disappears. Yeah. Got it. No, again, this is great, man. Really, really filling in kind of the little like gaps in my knowledge on this. So this is great. Yeah.
Yeah. So so the yi hat would be this vector here. It's sigmoid of the logits, so it would just be this vector.
Yeah.
Okay, so that's the cross entropy. Some logarithms
Oh,
do
dude.
appear.
Yeah.
Sorry, go ahead.
Oh no, I was saying now with this, I'm pretty sure like I might be able to optimize this now, knowing that relationship. Hold on. No. I think we'll save that. Maybe we'll save that for another video.
Yeah, there's a couple things. Like, there's a few questions. Like, why do we use this? That's one question. The second one is how do we optimize this?
Yeah.
Right. Like we saw earlier, we saw when we were studying linear regression that you can actually find an exact solution. We use linear regression. With logistic regression, we're not so lucky. We can't find an exact solution. So we're kind of forced into using something like gradient descent.
Yeah.
Yeah, but that's fine. Yeah, I guess there's one thing you were asking about. Yeah, so again, sigmoid is okay. And it turns out
Yes.
by just some miracle that's the derivative of sigmoid. So if we take a derivative, it's actually like very simple in terms of sigmoid.
Yeah.
It's just kind of like a miracle, I guess.
Yes. Yeah. And this is why the optimization is actually so not that bad.
Right. So if you plug in like yi hat equals sigmoid of z, then
Hold on. Yeah. So if you plug in that
you,
uh
you can
y
use
I
this
hat
formula to
equals
simplify
the
things.
sigmoid, yeah, equals just the sigmoid function of z. Yeah.
Mhm.
Then we get to that really, really nice kind of optimization at the end where everything cancels nice and neat.
Yeah, kind of. I mean, it's not the neatest thing, but at least it does make our lives a little easier to know this formula.
Yeah. Yeah. Well, yeah. It's damn near impossible to kind of do without that.
Well, you could
I
always do
mean,
it numerically.
yeah. Yeah.
But yeah.
Okay. Yeah, I think that's kind of it there for logistic regression. I just wanted to
I
get to
guess
the
there's one
class.
more thing I
Oh yeah.
thought you had
Yeah.
asked earlier was like so this is actually turns out to be like we saw with the linear regression that it was actually a maximum likelihood estimate.
Yes. Yeah.
This also is a maximum likelihood estimate. So that's probably something I could help you with. So let's take a look at that one. Yeah, so let's look at MLE. So suppose that the truth is 1. The truth is y equals 1.
Hmm.
That in dollar signs. So then what's the probability that, like what's like and suppose yeah, so basically if we guess that the probability was like 0.62, then
Yeah.
like 62% of the time we're going to get it right.
Yes.
That kind of makes sense. So like what's like maybe that's the right way to think about it. So like what's the probability we predict correctly? And it's exactly going to be y hat.
Yeah.
Does that make sense?
Yeah.
And then so what about if y equals 0?
And we predict 0.66. It's going to be 1 minus the probability.
Yeah, 1 minus probability, exactly.
Yeah.
So there we go. Let's keep that. That's going to be staying. Okay, so if
Mhm.
y is 1, the probability we predict correctly is y hat, and if y is 0, the probability we predict correctly is 1 minus y hat.
And that
So,
follows from the above equation as well, correct?
um,
Well, the log thing does. To me, it's like it almost follows like the equation we had up top, where like the first half leaves and you're just left with.
well, here, I
Um,
can connect the two, but it's not super obvious, so let me do this. So the
okay.
probability that we guess correctly in both cases. So I'm going to just write it out because it's a little tricky, and then we'll see
Mhm.
why it's this. The y. Yeah, there we go. So this is a formula I think you had showed me earlier, and this is kind of
Yes.
weird. And it
Yeah.
looks very strange, but if y is 1, then the second term, the 1 minus y, and the exponent is 0.
Yeah.
And so this whole thing, anything to the 0th power is 1.
Yeah.
So the second term would be 1. So let's actually write that. So
Yeah.
yeah,
Yeah.
we can
No.
write
No.
it.
Yeah. No. It just becomes y hat to the y.
Right. But if y is 1, so let's just do it. If y is 1,
Yeah.
y is 1, this. Y equals 1, then the above is just y hat, right?
Yeah.
And if y is 0, then the above is 1 minus y hat. Again, the same logic. If y is 0, the first term is 1, and then the second term is going to be 1 minus y hat. So
Yeah.
this should look familiar to this guy here. So this kind of equation, this y hat to the y and all that, is just a complicated way of writing this logic out, basically.
Yes.
So literally, this is like the probability that we guess correctly is actually equal to this. And the reason why it's equal to this is because of this logic where we say, we basically divide it into 2 cases and check that it agrees with what we originally had said.
Yeah. And then we just take the log of that gets us to the cross entropy.
Yeah, it turns out if you take the log of this, yeah, that gets you basically to the cross entropy. Yeah.
Yeah. And we're taking the sum because of what?
Yeah. So what does n represent in if this were
The
like a
number
data
of
science problem?
instances. The
Yeah,
number
the
of
number of
instances
instances.
data set. Yeah.
Right.
Oh
And
yeah,
then
because
this
we're
is
trying
just
to
a single
minimize.
instance.
Yeah, we're trying to minimize the overall error. So that's
That's
why
right.
we're taking the sum. Yeah.
Yeah, this whole logic we focus on one specific instance, and then when we work all together, we sum up. And exactly, so you see that there's like yi log of yi hat and all that. That's literally just
Yeah.
taking log of this thing, this
Yeah.
product.
Yeah. That's literally what we're doing is we just take the log of this. And that because on the
And we're trying to maximize this product because we're trying to maximize the probability that we guess correctly. Whereas here, there's a negative sign and we usually try to minimize. So that's where the negative comes from when we swap from a
yes.
maximum to a minimum.
Yeah, got that as well.
So yeah, this MLE is actually a lot easier to derive than the Gaussian one for linear regression. Turns out.
Oh hell yeah, dude. Yeah, no, this is like again, this I can actually whiteboard, like given the derivative of like the sigmoid and everything. Like I've been told by a couple of people that it is good to know to whiteboard the solution. Again, for like non-PhD data science people, this is our question that lets them know that we actually went to our linear algebra class and we can kind of do some stuff. Or not really linear algebra.
But it's the same logic for the linear regression and the normal one. It's the same exact logic. It's just this formula is a lot more complicated. But you do the same trick. You write this formula and then you take a derivative and all that.
Oh yeah. No, you're saying for the linear regression, it's a lot more complicated.
It's a lot more complicated, but it's the same pattern.
Yeah.
But yeah, perfect. So this
Cool.
This is a very quick overview of logistic regression and cross entropy. But yeah, that's fine.
Yeah. All right.
Cool.
Awesome, man. Thanks so much. So again, we got covered what I thought we'd do. Decision trees and neural nets on Wednesday.